Hello, I'm Scott Cameron, and I want to welcome you to today's webinar, where the topic is the Cascadia Megaquake, Current Science on Earthquake Source and Related Hazards. Now, this is the first in a three-part series that Beezer will host on the Cascadia Megaquake. Our speakers for today are Dr. Kelin Wang of the Geological Survey of Canada and Dr. Joan Gomberg of the U.S. Geological Survey and University of Washington. This webinar series addresses a key question. Is the West Coast ready for a 9.0 magnitude earthquake followed by a large tsunami? Data collected over the last 30 years show that multiple giant earthquakes and associated local tsunamis have struck the Pacific Northwest for at least the past 10,000 years. The 800-mile Cascadia subduction zone, which extends from northern California along Washington, Oregon, to southern British Columbia, is the main source of these earthquakes and accompanying tsunamis. This three-part webinar series will look at the science and engineering associated with the earthquake source, the hazards, current strategies to mitigate loss of life, and the emerging opportunities in early warning and reducing uncertainty. Now, we have a few housekeeping items before we get started. First, the audio for today's event will be streamed through your computer speakers. We will be taking questions through the Q&A box located in the lower right-hand side of your screen. Simply type your question in the box at any time and click send. We'll ask you to leave the box set to sending your questions to all panelists. Second, this webinar is being recorded. Please understand that any questions you may submit may be read aloud and included in our recording. A link to the recording as well as a copy of the slides will be posted on our website within the next week or so. Third, if you have any technical issues during the event, please contact WebEx Technical Support at 1-866-229-3239. Once again, that number for technical support is 1-866-229-3239. And with that, I'd like to turn things over to our first speaker, Dr. Kelin Wang.
Thank you, Scott. Thank you, everyone, for attending the webinar. I will start the webinar series by discussing some of the scientific issues. And Dr. Gomberg, after me, will address some of the hazard implications. The Cascadia subduction zone is where the oceanic plate, Hornifical plate, is subducting beneath the continental North America plate. And here, the subduction zone produces different types of earthquakes. It produces earthquakes in the overriding plate, and like in 1946 on Vancouver Island. It also produces earthquakes in the downgoing plate, like more recently the Nisqually earthquake, which caused a lot of damage in the Seattle area. But in this webinar series, what we will address will be the largest type of all these earthquakes. That is the event that occurs along the interface between the two plates. A lot of research has been conducted on the Cascadia subduction zone and its big earthquakes over the past few decades. And I will summarize what we have learned. And we have learned a lot, but I'd like to mention that what we know are the main four things here. One is Cascadia margin is a very typical place for producing giant earthquakes. There's no surprise. It has all the components. And the last big event occurred in 1700. And similar events occurred every few centuries in the past. And we also know now the system is building up energy for the next big one. So let's start with why Cascadia is typical for giant earthquakes. And the Earth has a very hot interior, and the most outside layer on the order of about 100 kilometers is our lithosphere. And this is where the tectonic plates motion occurs. Because the interior is very hot, the mantle will convect, and mantle convection will cause plate motion. And in plate tectonics, there are different boundaries of plates. One particular type that we most worry about is the subduction zone, where one plate goes beneath the other. But the subduction of one plate beneath the other is not always smooth. And very often, the interface gets stuck, what we call locked. When it's locked and the upper plate is being compressed like a spring, building up energy, it's being shortened in that direction. And once the fault cannot hold anymore, it'll break. And the energy built up will be released to produce ground shaking, and it will cause the subsidence of the coastal area. It will raise the seafloor to produce tsunamis. There are many subduction zones around the world, like around the Pacific. You see these dots, and these are earthquake locations. Most of them are produced by subduction zones. Among them, there are some very big ones, what we call giant earthquakes, magnitude 9 or above. These include the 1964 Alaska, 1960 Chile, and more recently, 2004, the Sumatra earthquake, and 2011 earthquake in Japan. Cascadia is, unfortunately, is one of them. Without a written record along the Cascadia margin, how do we know earthquake happened in the past? First, we learn it from coastal geology. And remember, when the plate is locked and we have this pattern, upper panels left, once the lock zone breaks to produce an earthquake, the coast will subside. It will leave some records, like the mud layer, the peat layer you see on your right-hand side, and used to be grass, and it was it turned into mud like this because of sudden subsidence. And the geologists can tell the subsidence must be sudden. It wasn't a gradual event, so it's good evidence for an earthquake. And we have evidence like this along the margin, and in many places. And how do we know the exact date of the last event? And we know it from historical records in Japan. In 1700, and there was a tsunami in Japan, caused a lot of damage along the coast, but there was no local earthquake preceding it. The Japanese know very well tsunamis are caused by earthquakes. So they wrote in their record then, and this tsunami caused a lot of damage, but its source is unknown. It needs to be studied by future generations. Now the future generations, after some research and understand the earthquake causing that tsunami was at the Cascadia margin. That's how we knew the exact date and even timing of that earthquake. And how often did it happen in the past? Again, we come back to our own local coast. Now we study the offshore sediments. And every time a big earthquake occurs, the sediments on the continental shelf will be shaken loose, and they will float downhill to the deep sea to cause turbidites. And these turbidite deposits serve as records of past earthquakes. So scientists will take course with instruments like this to your left, and will go offshore and take course in different places and analyze these cores. The results of the analysis are summarized in a simple way as this. It turned out the Cascadia subduction zone has a tendency to produce very large earthquakes that rupture the whole margin, and something like 1,000 kilometers up and down the coast, like the picture to your left. And the large earthquakes happens about every 500 years. There were also other types of smaller events. In particular, there's a proposal that more but smaller events would occur in the south of California. So we have complex pattern, but the subduction does have tendency to produce very large earthquakes. So we know what happened in the past and how often it happened in the past, and how do we know what the megathrust subduction zone is doing today to prepare for the next event. And we have a lot of instruments and a lot of observations and modeling to address this question. I think one of the most convincing lines of evidence is the geodetic monitoring. Monitoring crustal deformation or strain energy built up along the margin, the Cascadia margin, due to the locked megathrust, started in the early 90s. By 1994, we had our first continuous monitoring system along the Cascadia margin, the fourth size in Canada. And this is what we have today. And in addition to all these GPS stations, we also have numerous temporary GPS sites and numerous seismic stations that provide good information. So what have you learned from all this GPS monitoring? Now we know all these sites are moving east and at a certain velocity. And that's a solid evidence for the locking of the megathrust fault. And a better way of summarizing this energy buildup is to our right-hand side, and the data, the velocities of a GPS sites can be converted into what we call strain rates. Strain rates means when you see a symbol of this length, and that means and 2 points 100 kilometers apart get closer to each other by about 5 centimeters every decade. So over 500 years, that's 5 meters, and that will be recovered by the next earthquake. So this is what as I said earlier, the upper plate is like a spring being compressed to build up energy. Okay, now we know from coastal geology and Japanese record about the last event in 1700, and we know what's going on today. How do we know the system evolved from 300 years ago to today's situation? To understand this, we look around the world and to learn from other subduction zones that produce giant earthquakes. It turned out the earthquake cycle will have a certain pattern. At first, shortly after the earthquake, all the stations will move seaward, continue to move seaward. And then after a few decades, like what we are seeing in Alaska and Chile, and coastal stations and inland stations will move towards each other, the opposing motion. And eventually, all the stations will move landward. So by using a physical theory of physics, and we can develop a numerical model, a computer model, to model this process for Cascadia. And for Cascadia, a couple of years after earthquake, where the Queen Anne's War was taking place, all our GPS stations today would have been moving west towards the ocean. By the time the first people from European arrived on our coast, and our coast would have been experiencing opposing motion like this. And by the time Captain Cook arrived, and all the stations would have already turned around. And Lewis and Clark would have seen the same thing had GPS been available at the time. Today, we are seeing more or less the same pattern, but the speed of motion is a bit slower. And that slowing down also contains important scientific information. And not only we understand the evolution of the crustal deformation and strain energy built up, and more recently, we also discovered a phenomenon that indicates the fault is indeed still active. The shallow part of the fault that will produce the next earthquake is currently locked, but a deeper part will move from time to time, on the order of about every year, will move by a few centimeters, accompanied by a little seismic tremor. They serve as a reminder that the fault is active. It's not is sleeping, but it's still getting ready for a big event. So let's also further discuss what we do not yet know, but we really hope to know. And a lot of things are still being studied. There's many questions to be answered, but I like to highlight three what I consider the most important ones. The first is what we know the Cascadia fault is locked and building energy, but we don't know to what degree exactly, whether it's 100% locked or is partially locked, and that's something quite important in terms of hazard implication. And also, we really want to know, will the rupture breach the seafloor? That is an important question in terms of tsunami generation. We also would like to know, and how does seismic behavior vary along the Cascadia margin? That's also important in terms of hazard and risk assessment. Okay, the first question, and to what degree is megathrust locked? And from the GPS data I showed earlier, now you see to our left, and we can construct models of megathrust locking. And so if you see red here to your left, and the fault is fully locked. From the same data, we can build models, two models like this that look quite different. They both show some locking, but the degree of locking is very different. And the reason is land-based observations do not have provide enough information for the far offshore area. But currently, our assumption is more for the shallow and narrow lock zone as fully locked. And the reason is the temperature for this subduction is quite high, and it tends to confine rupture to a shallow area. And the other reason is the fault is quite quiet. That means it does not produce a lot of small earthquakes. Only a few of them are off Oregon are confirmed this earthquake to have happened on the megathrust. They are magnitude 3 or a little larger. And normally, if the fault is creeping, not fully locked, we expect some small earthquakes. The lack of earthquakes along the margin, most of the margin, leads us to assume that the fault is fully locked. But either it's narrow or fully locked, and these are assumptions. These are good assumptions based on what we understand about the physics of the matter. But we still do not have the final answer until we truly observe the locking state. So how do we get a true answer? We have to go offshore. We have to conduct offshore monitoring. The next question is, will the rupture breach the seafloor? And a megathrust earthquake can produce tsunamis in different ways. It can produce tsunami without breaching the seafloor, or it can produce tsunami by diverting rupture to another fault called splay fault. But what really surprised me was what happened in Japan in 2011. The rupture went all the way to the trench, and the sloping seafloor, the motion of the sloping seafloor, caused a devastating tsunami shown to your right. And so that raises an important question. Will Cascadia behave the same way? And we are busy investigating this issue. Cascadia is different. We have a lot of sediment offshore, different from Japan. So there's a possibility that other faults can be involved. That's still part of the question and to be studied. The last question we really hope to have answer for is, how does seismic behavior vary along Cascadia? What you see is the latest model for the rupture scenario of the 1700 earthquake. We have these patches and constrained by microfossil studies along the coast. And it's a good question whether this the pattern is random with time. Every earthquake will behave somewhat differently, or the high slip, low slip zones are controlled by geology. That means they will be persistent in different earthquakes. And we are trying to answer this question, but it's interesting to see some intriguing correlations with other processes, such as the ETS, behavior, episodic tremor and slip I mentioned earlier. They seem to have a long straight variation, and the segmentation of ETS seems to have some correlation with the rupture pattern. And also there's some correlation with assumed subducting seamounts and correlation with rupture lengths derived from offshore turbidites. So in summary, what we have learned is Cascadia is a very typical place for giant earthquakes. The last one, magnitude 9, occurred in 1700. And similar events occurred every few hundred years in the past, and we know for sure now the locked fault is building up energy for the next big one. And what we do not know, but are still investigating, is to what degree the fault is locked, and will the rupture breach the seafloor, and how will the seismic behavior vary along Cascadia. Thank you.
Thank you. Thank you, Kelin. Over to Joan.
All right, thank you. Well, what I'd like to do now is explain to you snapshots, anyway, about how this science makes its way into our understanding of the hazard these giant earthquakes pose. In addition, these earthquakes initiate a cascade of other phenomena which in themselves are also hazardous, and those are illustrated here: other earthquakes, landslides, volcanic eruptions, and again, tsunamis. And I'm going to illustrate some examples of these and highlight some of the open questions that we have about the hazard. Well, the first other hazard are other earthquakes. We need to understand these both because while we're waiting for this giant earthquake, these are going to happen on their own, and they will comprise the aftershock sequence following a giant earthquake. The setting in which earthquakes occur determine their characteristics, so we need to think about them in their particular setting. We'll first look at those that occur in the downgoing plate, the subducting plate. The first type occurs right at the trench where the plate begins to bend as it goes down. These are called outer rise earthquakes. We know from earthquakes elsewhere that these can be very large, and because they're so shallow, they're very effective at generating tsunamis. We know almost nothing about these in Cascadia, and they're basically just ignored in hazard assessments. We also get small earthquakes within the downgoing plate at shallow depths, but these tend not to be very large, and nobody lives nearby, so we also really don't pay much attention to these from the perspective of hazard. And finally, as Kelin mentioned, we have earthquakes deep in the downgoing plate. These are the most common earthquakes in Cascadia. You can pretty much expect that in your lifetime, at least if you live in the Puget Sound region, you will experience one of these events, about an 84% chance of a magnitude 6.5 or greater in 50 years. Because these are beneath the populated areas, these can be damaging, but their depth puts them at some distance relative to a shallow event, and they tend not to generate very many aftershocks for some unknown reason. We also think about earthquakes in the overriding plate. Those are shown here. Those tend to be smaller than the megathrust events, but locally can be more hazardous because they're closer, they're shallow. Each of these faults individually tends only to make an earthquake on timescales of thousands of years, but there are many faults. So the likelihood of an earthquake, a sizable earthquake, again, and I focus on the Puget Sound region because that's where I live and I had the most examples, but that's about the same likelihood of occurrence as a megathrust event. And finally, the great earthquakes themselves. And as Kelin mentioned, these occur roughly every 500 years. And one of the things that's enigmatic about Cascadia is that other than these giant earthquakes, the plate interface does not make smaller earthquakes. And this is pretty unique to Cascadia. Well, one of the questions we need to address to assess the long-term hazard is how often these events occur. Kelin touched on this. The evidence for this comes from two principal sources. One gathered offshore, onshore is shown on the left, from coastal evidence of uplift and subsidence, and as well as tsunami deposits. That gives a pretty consistent estimate of about a 500-year recurrence time throughout all of Cascadia. If we look to the offshore record that Kelin mentioned, the turbidite record that's shown on the right, and as he mentioned, what we find is that it appears that earthquakes, these interface earthquakes, occur more frequently in the south. Well, reconciling this difference is really important from a hazard perspective. The difference between these two models, if you like, or pictures, in southern Cascadia is a shaking hazard that differs by about 40%. So if you're doing, in terms of mitigating construction costs, that is very significant. And this is something that we're actively working on trying to understand. Another thing that we need to understand when considering the hazard is the shaking. It's the seismic waves or the shaking that does most of the damage. This is shown on the left here is a hypothetical distribution of fault motion during a great earthquake. The way that we think about this now, and this has really been learned in the last decade or so from earthquakes elsewhere, but we can think of it as a superposition of multiple earthquakes. We have one large earthquake that spans the entire fault zone with very large amounts of slip at shallow depth. Superposed on that are smaller earthquakes shown by the rectangles, which slip less. But it's the rate of slip that determines, to a large extent, the shaking. So if we look at the large scale, large amplitude slip, that occurs relatively slowly. It's good at generating tsunamis, but radiates shaking waves that oscillate too slowly to be very damaging to most structures. However, these smaller patches, which slip less, but they slip more rapidly, and those are what seem to radiate the rapid oscillations or high frequencies that buildings are sensitive to. Shown in these seismograms or records of ground shaking are what is predicted for these two types of earthquakes. The red are from just slip on the entire fault in two directions, the vertical on the south, on the bottom, and the horizontal motion on the top. And then when you add the slippage from these smaller added events, which slip faster, you get the result on the right. And it's this rapid motion that you can see in it that is what buildings are sensitive to and does the damage. Finally, the other thing that is important in understanding the shaking is the rocks beneath our feet. This is kind of an image of the subsurface beneath the Seattle area, sort of an ultrasound, showing the structure of the rock, the really hard rock. And this is where it's shallower, as from red to deeper is purple in the middle. So this is a big basin that is filled with softer sediments, and that basically acts like a giant bowl of Jell-O that shakes harder where the jello is. And to illustrate that, an experiment was done a number of years ago. These are, again, recordings of the ground shaking. This is from an explosion at different locations. All the locations in the lower half of the figure, and this is in two different horizontal directions, those locations in the outside the basin are shown in the lower half of the figure. Locations above the basin are shown at the top, and what you can clearly see is that the effect of those sediments is to prolong the shaking and amplify it. So a very significant effect in terms of the potential to do damage. Well, all this goes into a whole variety of products and with practical implications. Building codes is shown on the left. On the right is a high-resolution hazard map for the Seattle area that the city is using to prioritize its retrofitting of most vulnerable buildings. This kind of information was used to construct the design of the new Amazon campus, for example. It's shown in the photo in the middle. Well, now to look at some of the other cascading effects from these giant earthquakes. The first, as Kelin mentioned, they cause the ground to go up and down and stay that way for a very long time. This doesn't only happen in megathrust events, but also in crustal earthquakes. This is a picture from an area with really high-priced real estate in downtown Seattle. This land came up about 7 meters in a matter of seconds during a magnitude 7 crustal earthquake, fortunately about 1,100 years ago when real estate was not so valuable there. Well, if this is the same photo, a larger scale photo that Kelin showed, the ground also goes down over large scales in a megathrust event. This is a photograph from 1700. The photograph is recent. The ground dropped in the 1700 earthquake and killed all these trees. So clearly this subsidence has big effects on ecosystems and industries, in this case the timber industry, for example. Another cascading effect of these earthquakes are landslides. While landslides happen everywhere, subduction in Cascadia creates ideal conditions for landsliding. Shown here in this map are mapped landslide deposits in western Oregon by the red superposed on some of the infrastructure, highways, railroads, and pipelines. And shown in this bar graph are the number of landslides that would cover this infrastructure if there was an earthquake or these landslides actually moved by reasonable amounts. And you can see hundreds of these landslides would occur. Well, this is a picture of our most recent Cascadia landslide. This is the Oso landslide. It was clearly very devastating. This was not caused by an earthquake, but by rainfall. Indeed, rainfall is the most common trigger of landslides, and that creates a real problem for understanding what to expect in the next great earthquake. It's maybe surprising to realize that while we expect lots of landslides in the next giant earthquake, to date, no landslide has definitively been attributed to the 1700 earthquake. That's not because it didn't happen, but because it's very difficult to date old landslides. But there's new techniques now being developed using high-resolution topography, which is shown here. This is from the Oso region, where different landslides, which now have been dated using new methods, have been dated, their areas mapped, and their age seems to correlate with the roughness of the topography. So if we can determine that correlation, we could then use topographic maps to try to date landslides on a large scale. Another cascading phenomena are tsunamis. Kelin explained how these occur. One of the products that we use to assess and plan for these are inundation maps. As shown here, this is a map for Oregon, a community in Oregon. These are ground truth by looking at deposits from past tsunamis, as shown in this figure here. The tsunami deposits can be helpful in unraveling the record of past earthquakes. At the top is a schematic of what happens to the surface during a series of earthquakes and what the record of that is in the subsurface. As Kelin mentioned, each of these dark bands in here are left by deposits from tsunamis. And by digging these up and dating them, we can see that there was an earthquake in 1600, 1300, and 1700 AD. So these can actually be quite useful. Well, another product that are now possible on a local scale. This is a long-term hazard map, or shown as wave heights for the community of Seaside, Oregon. While this has high resolution, there's some key elements that are missing. This only accounts for tsunamis generated by a megathrust earthquake. One of the things that Kelin mentioned that's missing is the potential for these earthquakes to travel on what we call a splay fault, or a secondary fault. This is an image of the subsurface from a similar type of fault in Japan. And what we expect is that the rupture will propagate along the plate interface, the red line. But what happens instead sometimes is it travels up this secondary or splay faults. And because those are more steep, they're more effective at generating a tsunami. We know these occur in Cascadia. We don't know much about them, how likely they are to rupture in a giant earthquake. This is an example of a double cascade in which shaking unleashes a landslide, which in turn triggers a tsunami. This is a bathymetry from Prince William Sound in Alaska. What this shows scientists is that the shaking from the earthquake, the 1964 Alaska earthquake, shook loose a landslide, which in turn triggered a tsunami that at Chenega Village was larger than the tsunami from the earthquake itself and caused 23 fatalities. We would like to be able to forecast these in advance, and having bathymetry would allow us to do that. And finally, there's there's some evidence that giant earthquakes are linked to volcanic unrest, but the evidence is mixed. However, we do know that earthquakes play a role in volcanic eruptions. This is an example from Cascadia, the most recent Mount St. Helens eruption in 1980. The volcano was ripe for an eruption, but it was a local magnitude 5.1 earthquake that basically uncapped the volcano, that allowed all the pressure to be released and initiated the eruption. So there is certainly a link between, in this case, a local earthquake and an eruption. And with that, I'll stop and open it up for questions. Thank you.
Thanks to Joan and to Kelin for great talks. Really appreciate it. We're putting up a slide here that gives instructions about how you can put your Q&As into the queue here, and we have a few that have been submitted so far. I'm going to start out though with one of my own, and I guess that's the moderator's prerogative. Both of you have, and this is going to go to both of you. Both of you have identified some major uncertainties that still remain about the Cascadia megaquake, and identified some gaps in our scientific understanding. But what could we do in terms of critical research activities that would enable us to close those gaps and hopefully definitively answer the question or critically reduce the uncertainty? And over to you first, Kelin, and then to Joan. Same question.
Yeah, a lot of the questions that yet to be answered have to do with the observations from both sides of the rupture, and for now, almost all our observations are from the land side. We have seismometers, GPS stations, a lot of surveys. We know active faults, and in comparison, the offshore survey is very limited. Like the first unknown I mentioned is the degree of locking. It's such an important basic question, and the reason we are not that sure about the degree of locking is because we do not have observations near the fault, which is offshore. So I think these the offshore improving offshore observations will be probably one of the most important steps.
I agree with Kelin that our biggest source of unknowns and our biggest frontier, if you like, the place we're likely to learn the most, that will make the most difference, is in the offshore. In addition to the monitoring, things like what we've learned in some of the examples I showed, things like high-resolution bathymetry and imagery can tell us a lot about these processes like landsliding and splay faults and so forth. So the offshore, I think, is really the frontier where we need where we're going to learn the most and that will make the most difference.
Great, guys. Thank you. I'm going to take some of the questions that are coming in on the web. We have a couple that relate to issues of subsidence associated with a megaquake. One question asks, generally, what do the models predict about where subsidence should occur? And then there's a more directed question about what are the implications for potential quake-induced subsidence in the northern Willamette Valley. Kelin, can you take that first, and then Joan, can you add and expand on it?
Sure. Yeah, the observed or substance constrained by observations are from geological observations, like along the coast, almost everywhere along the margin, and they show different magnitudes, and roughly about 1 or 2 meters by an earthquake, and but with large uncertainties. So based on these observations and also comparison with earthquakes in other places, we can construct a model and that can fill the gaps where we do not have observations, right? So we basically see a pattern of subsidence along the coast, but the amount of subsidence can vary, and it depends on how far the rupture goes towards land. If it's mostly way offshore, is like smaller subsidence, and if it goes really over very deep, you even see uplift. So it is a complex question. We do have some models, but we still need to improve models to minimize the uncertainties.
And I don't really have much to add to that, nor can I really answer the question specifically about the Willamette Valley. Sorry.
Okay. Well, thanks for that. Thanks for taking that question. We have a question from another listener who's asking about potential linkages between a megaquake on the Cascadia subduction zone and potential ruptures related to it that might occur on the San Andreas fault system. Again, I'll let you both take that one, Kelin first, and then Joan.
Yeah, I think there was some interesting study by Chris Goldfinger and colleagues, and to link the earthquakes on the Cascadia margin and the San Andreas, and in theory we would expect some kind of linkage because of stress. When you have an earthquake and the stress in the lithosphere crust is perturbed, you tend to influence the neighboring area, and in some cases, and the fault in the neighborhood will be also put to a state close to failure, or even to failure. Fundamentally, this question is still a question of observations, right? You can produce models to show there's some effect, but the effect is the stress perturbation is not that large because of the configuration of the two margins or two faults. But if we have strong, good observations, we can better constrain the problem. I think what Chris and his colleagues were doing. I think that some research are worth to be pursued.
Yeah,
okay.
I'll just add that we know that while the calculated effects are relatively small, we also know observationally that these small effects can trigger, if you like, earthquakes at considerable distances. So it's certainly a question worth asking, and we can't definitively, we certainly can't rule it out, and it's a reasonable, plausible scenario.
Okay, I have a question now for Joan. Joan, you talked a little bit about tsunamis. How can the height of potential tsunamis be estimated? What goes into the estimates that go into inundation maps and tsunami forecasts, particularly for Cascadia?
What has a big effect on these is the bathymetry or the topography of the seafloor, particularly the local at the local scale. That's one in terms of modeling it, and the models are now quite sophisticated if you have good bathymetry and topography. The unknown, and then those models are ground truth, if you like, as in the figure, by going out and actually looking for deposits from past tsunamis. Did the water actually reach as high as the model suggests? The unknowns certainly in the forecasts are these higher resolution features like splay faults, the potential for landslide-induced tsunamis, which add to the main earthquake tsunami and can be very significant locally. So currently, the forecasts or inundation maps and so forth only consider the earthquake, the main earthquake itself, and not these secondary sources.
Okay.
Yeah, can I add something?
Sure.
Too? Yeah. What Dr. Joan, Dr. Gomberg said is quite right. But what I like to add is there's a difference between tsunamis generated by earthquakes elsewhere or tsunamis generated locally by the Cascadia earthquake. And for earthquakes or generated elsewhere like Alaska, Japan, and when by the wave comes here, and what's important for modeling the inundation, and what we need to know is mainly the size of the earthquake on the other side of the ocean. For local Cascadia earthquake, and it's really important to understand the details of the earthquake source, the rupture, how the rupture distributed along the fault, and mostly in the shallow part or deep part, how it varies along strike, and how it tapers in different directions. And all these are source questions are extremely important for designing local tsunami models. And unfortunately, we have not observed an earthquake on our own margin. So what we have done is to learn from other margins and to use the applied experience to our own places, and we use our best knowledge to construct these source models. And these models are based on good assumptions, but with more observations, these models will be improved, will change.
Great. Thanks for that. Here's a question. just to get to probabilities, I heard several references to probabilities for some of the smaller quakes that occur, like the Nisqually type quakes. But what should the public be thinking of in terms of the probability in the next 50 years for a Cascadia megaquake? And I guess I'd turn that to Joan first and then to Kelin.
Well, the estimates, the official estimates, those that go into, say, the seismic hazard maps, is about a 10 to 15% chance in 50 years of a high 8 to 9 type magnitude earthquake.
Wow. Okay.
Well, I don't have much to add. It's a little bit beyond my own expertise, so I think what Joan just said sounds reasonable.
Okay. Okay. What clearly one of the things that we've heard a lot about, particularly from researchers in California, is progress on early warning technologies. What's going on? What are the opportunities for early warning technologies relative to a Cascadia megaquake? Maybe Kelin, can you take that one first?
Well, maybe Joan can talk about the online part, so I'll add something about offshore.
Okay.
Is that okay?
Yep.
Sure.
So.
Oh, do you want me to go first?
I think you go first, Joan.
Yeah. Sorry.
So there is now a West Coast early warning system which runs from Southern California, border to border. It is in, I guess you would call it test phase, where there are some, it's not publicly available, but there are users who are trying it out. This, again, covers the challenges. It covers all of California and Cascadia. There's some challenges in Cascadia that, again, we don't have a lot of practice, but they're certainly trying to put it to the test as much as possible, in that a lot of the earthquake activity and the ruptures will occur offshore where we don't have instrumentation. There's also, we have a greater, than in California, relative to a greater complexity of earthquake types. So you need to be, in an early warning system, you need to be able to identify, yes, this is indeed a great Cascadia earthquake and not a local event, a crustal earthquake, for example. And you need to do that really quickly. And there are a lot more choices here about what type of earthquake it might be. But those things are, again, they're being worked on, and the system within the next couple of years, certainly, the plan is that it will be publicly available.
Yeah, I think we are making a lot of progress on land in building up a system like that, and we're also making some progress offshore. And we don't have a lot of facilities offshore. Currently, we have 2 cable systems, Neptune Canada and Ocean Observatories Initiative in the U.S. of Oregon, and they cover very small parts of the Cascadia margin. And in early warning, if you want to warn against damaging seismic waves, you want to detect the fast traveling P wave and use these P waves to warn against more damaging surface waves. And so you want to also you want to, like Joan said, you want to distinguish between different types of earthquakes. So we have some near field observations offshore. It'll improve the detectability tremendously. And also, we like to have some warning for tsunami, right? Of course, ground shaking would be the most direct warning for the ensuing tsunami, but we have some instrumentation, and we have some more quantitative information, and that will also be very valuable. So there is a proposal to try to develop monitoring system offshore, not only for scientific purpose, but also for warning purposes. But we still have a long way to go. Securing funding is an important issue.
Great. Thanks for that answer. We have several questions that are somewhat linked about tsunamis and how related to a Cascadia event and to the 1700 event and how far they might have gone. One of the questions is with a local tsunami on the coast related to the megathrust, how long will it take for that tsunami to reach shore? How much time will people have to react? And then a follow-up question is there any evidence that those tsunamis will propagate into Vancouver, Puget Sound, reach the inland bodies of water as well? So maybe, Joan, you take that first, and Kelin, can you follow up?
Okay, this is not my expertise, but I'll tell you what I know. My understanding is that on roughly it take about, and again, it depends where the earthquake starts, about 15 to 20 minutes for the first wave to hit the shore, keeping in mind that waves can come in for hours afterwards. The second question is, yes, there will be energy waves that make it into Puget Sound and affect Vancouver and, again, all the communities in Puget Sound.
Yeah, what I can add is we also need to worry about the local amplification effect. And if you look at your map and the distance from what we call the deformation front, where basically the downlip end of the continental slope, and the distance from that to your coastline, that basically tells you how much time you have. If it's really close, you have very little time. It can be short as 10 minutes. If it's farther away, it can be 20 minutes. So on the order of 15, 20 minutes. But tsunami waves can get amplified by local structure, local topography, and these require experts to model them in great detail, and that's something, and we're missing a lot. So we do need the detailed bathymetry and to model all these local effects, amplification, like when a wave travels into a Puget Sound, and the energy is pretty small. And so it's not as big as on the West Coast, but still local topography, bathymetry can cause some amplification. So all these needs to be modeled.
Just another quick an aside to that is we think of all the hazard from tsunamis as being the wave and inundation, but tsunamis also can set up very strong currents. So, as an example, the 2011 Tohoku earthquake in Japan did damage in the harbor at offshore California, and I'm having a senior moment, the name of the community. At any rate, set up strong currents in the harbor, and those can be damaging. So it's not just the wave. Fortunately, those kinds of things now, they're beginning to be able to model those and forecast where they might happen. Crescent City, thanks.
Crescent City, yeah. Thank you for that. Maybe one last question. You mentioned the Japan earthquake and tsunami. What were the one or two key things that we learned from that are changing how we view Cascadia? Both of you.
Well, maybe I'll go first. I think the hardest lesson from Japan is we need to be ready for surprises. For the longest time, and with Japanese research and monitoring, and we developed the recognition that the Japan Trench subduction zone had a tendency to produce magnitude 8 or 8.5 earthquakes, but what actually happened really surprised us. That means we still have a lot to learn. So that's the hardest lesson. And the other is the way the rupture happened in the shallow part of fault. That really surprises too. And as I mentioned in my talk, it raised a question for Cascadia. And if the rupture occurs in the shallow part of fault, in the deeper water, it can cause a greater tsunami. And so that's something how it happened in that way with like 50, 60 meters slip in the shallow part, it was never anticipated. So that was something we learned, a hard lesson we learned.
Well, I'll just add, since I guess this is the last question, and
yes.
end on a positive note, is what we tend to focus on all the terrible things that happen, but I think, and I can't quote the numbers, but I think we did learn in the Tohoku earthquake, if you look at the damage and injuries and fatalities from the shaking, that it shows that mitigation really, and the effectiveness of the early warning system they have, that mitigation and preparation in advance really does pay off. Given the size of the earthquake, and again, from the shaking perspective, it was a lot better than it could have been, and that's due to the preparations that had been made.
Yeah,
excellent point.
Good story. Hey, it looks like that's all the time we're going to have for questions today. So I want to thank both of you for being great troopers with us today. As a reminder to the audience, parts 2 and 3 in the Cascadia Megaquake series will be coming up later this year. Details will be posted on the Beezer website, and they'll be shared by email as well, I think, to all the participants in this call. A copy of today's recording and the slides will both be posted on our website within the next week or so. And with that, I'd like to thank our speakers, Drs. Wang and Gomberg, and thank all of you for joining us today. Have a great day.
Thank you.
Thank you.